Hello, Jade. I thought I'd spend some time talking to you. You're much more sane than anyone else I listen to. And I got a book here, look. It's really good, and I haven't read it for ages because I've been kind of distracted. I should just be getting on with it because the guy was great. You can tell he was great, look. And Jade was making this video. Sorry, I'm talking quietly because it's a bit early in the morning. My housemates are sleeping. I got my old physics book, which I did my course in, and I thought if I looked at it, I might remember some of the stuff. But it's very complicated. It uses, I've got to get my glass. This belonged to Benjamin Carter, who was at Nottingham, and whose phone number was, I'm not going to say in case he still has the phone. Here's a flow diagram, look. Wow. This is the flow of ideas, not the flow of electromagnetism. Except, if you think about it, if you're a reductionist physicist, then the flow of ideas ought to be a product of some sort of electromagnetic stuff with a bit of gravity. But look, here's the gravity. There's all these things at the bottom. And the flow is force and energy in electrostatics, dielectrics, electrostatic field calculations, steady currents and magnetic fields, magnetic materials, then electromagnetic induction and magnetic energy, alternating currents and transients, linear circuits, transmission lines. Waveguides, generation of electromagnetic waves, electromagnetism and special relativity. And underneath electromagnetic induction and magnetic energy is Maxwell's equations, electromagnetic waves, the generation of electromagnetic waves. So it's interesting, these things are all experiments. These are all laboratory equipment. And and these are theories. And these theories of electromagnetic waves are particular solutions to Maxwell's equations. And linear circuits are a certain type of circuit, a very special kind of circuit that you can analyze easily. And particularly, you can analyze it in terms of these alternating currents and changes of current. So an alternating current is a smoothly varying current with time that's going one way and then the other. So it's a sort of simple harmonic current. And transients are little bumps which you, with this linear approximation, you can treat the bump as an infinite series of alternating simple harmonic currents that have all been added together, and they can produce any shape in the middle. Well, that's Fourier series and things, I think. So I'm guessing that linear circuits are ones that are whose behavior can be analyzed by looking at the way they respond to particular frequencies. And then as you go up and up and up, you kind of get to well, it's not really up, is it? I don't know. The force and the top three are force and energy in electrostatics. That's number one. So that's the first thing the book treats. And then dielectrics, which are materials made of dipoles, which have, they like a positive charge and a negative charge connected together, so that lots of molecules are like this. If you have a, is that right? If you have an ion, you have a positive nucleus and a negative shell, except they don't balance out. The whole thing has a net. How does it work? An ion, it has an extra electron. Is that right? Can't even remember that. I can't remember the difference between an ion and a cation. Dielectrics, polarization, 49. A nucleus with charge plus Ze and an electron cloud. An isolated atom. The electric field displaces the electron cloud. Okay, so it's just an ordinary atom with a... Right, I remember now. The idea is that the center of mass of the electron cloud and the center of mass of the nucleus with its positive charge that's exactly opposite are not in the same place. So you get something like it's not to do with ionization. But I wonder how ionization comes into it. Does it just increase the difference between the charges or decrease it? I don't think it talks about dipoles made of ions and cations. Maybe the theory is a bit too complicated. So these dipoles you then think of as a thing like this. A little bar connecting a positive and negative charge. And then you can do some maths and work out what is P. Gosh, I can't remember anything. P is the dipole moment. And a moment, I can't remember what a moment is. I thought a moment was something to do with kind of the way things balance. And they've weighted one way or another. I've just been listening to people talking about physics too much, I think. Physics seems to have been a very, how any woman ever managed to stay interested in physics, I really don't know, because it just seems like a whole lot of male egos in some kind of intellectual orgy. It's disgusting. Anyway, here's my idea of physics. When you have a magnetic field, in all the books they draw it as these lines, and the density of these lines they call lines of flux. The density of the lines reduces as you get further away from the poles of the magnet. But at the poles it's concentrated. And the magnetic flux is really just a magnetic flux, because if you sprinkle iron filings on a page and put a magnet underneath, you can see these lines appear. But when you think about what makes a particular line of filings line up in that place, it's really only because there were other filings that lined up in that place. And the only kind of lining force acting on filings is through the magnetic response of the filings to each other in that place. So they all kind of group together as best they can, because they're little magnetic particles themselves. And if you kind of think about that, that's got to make up some lines, and the weaker the field, the further apart are these lines. So I'm guessing that it must be see, you typically need to shake the sheet a little bit to shuffle them. And then they line themselves up. But I'm not sure what would happen if you lined up if you put a magnet at a certain point and a certain orientation underneath the page, and then saw one of the field lines, and you say you marked it with a pencil, one of the loops, whether you could then take the magnet away from under the page and then shuffle all the little filings so that they were all on just one loop. They were all like on that inside one. And if you then put the magnet back, I can't imagine any of them would go anywhere else. They would all just sit on that place. And I think you accept that maybe that place would be a slightly different place because the other lines aren't there. Do you see what I mean? I think that this is a good place for filings to be. It's an energy minimum because anywhere in here they're pulled this way or that way, and anywhere in here they're pulled this way or that way, and anywhere in here they're obviously pushed out. I don't know how it works. You don't do these things at school. All you do is put the filings on the page and the teacher says, look, there's the magnetic field lines. But if you think about where the magnetic field lines actually are when the iron filings aren't there, I can't see why there's be any reason the lines would be in some particular place. So the magnetic field lines are only where they are because of where the iron filings are. And the iron filings are only where they are because of the magnetic field is where it's at. So it's a loop. It's a causal loop, like the Buddhists talk about pratitya samutpada, dependent co-arising. This happens because of that, and that happens because of this, and the two. And with the cessation of that comes the cessation of this. So I bought some charcoal pencils, and I was having fun trying out different ways of drawing lines. I think actually that one looks better. But I think if I practice with my pencils a bit more, I'll be able to draw nicer fuzzy lines of filings. I should probably buy some filings and a magnet from eBay and try this out. But I don't want too much stuff in my life. I've really got far too much. It's my cup of tea. So I'm sorry, I'm not very awake with this video. but I was trying to think about how we can interpret this idea of yours. And I was thinking that when you identify these, I drew when I was talking about the orientation of the relative orientation of the toruses, the tori. But then I realized that there's a kind of abstract space as well, because each of the tori could be thought of as that whole plane, and that whole plane, and that whole plane, except in the torus, that and that are the same place, and that are in the same place because it's wrapped up. But quite how you this is topology, I think, that we're doing here. Quite how you connect those three. I don't know. Because Jade has made a really nice video on the shape of space, where she talks about this, that if you walk off, if you have a point moving on in this plane and it moves off here, it comes on here, and when it moves off at the top here, it comes on at the bottom here. And similarly in this plane, if it moves off here, it comes on here. And if it moves off here, it comes on here. Because if it moves off here, it comes on here. So there's a seam. There's a seam here and a seam here. And you kind of need to show on this picture where those seams are. There'll be a and a here, which are these edges. Is that B? Yeah. Somewhere we need dotted lines on here showing which of these is which, and we need long dots to show the long axis, and we need short dots to show the short axis. But I'm not sure. Toby will know all this. Is this a three-dimensional torus, or is it a six-dimensional torus that we're talking about? Because I've somehow come up with what looks like a three-dimensional space, but it has two dimensions in each plane. But I guess because there's an intersection between each plane, there's a redundancy in that in one plane, two of the coordinates identify somehow with coordinates in the other. There's a linear dependence. And I'm not quite sure how it works, whether we've actually got three planes with I don't know. There's a way of talking about this in linear algebra. Where you have this idea of vectors spanning a space. So if you have two vectors in 3 space, in a sense these vectors span a plane. So the 3 space is this room, and these two vectors are spanning a plane in that room, because you can add multiples of one to multiples of the other, and halves and quarters of one to halves and quarters of the other, and you can reach any point on the plane that contains these two vectors, and that's called a subspace. So within this room there are these infinite number of subspaces that all span together the entire room. Because if you have a perpendicular to that subspace, then that can be your third vector. So in some sense, although we've got 2 coordinates on each to identify a point on any torus, you see, individually, normally if you can have don't you need 2 radii to specify a torus? Can you fill a room with... No, because they're always redundant coordinates. You have the main radius of the torus, the large radius, and the small radius. Although in the case of a kind of pinched sphere, the large and the small radius are the same. But then you don't have a hole. So that's a bit of a funny one. But usually if you have a hole, then one of the radii must be greater than the other. So you have a large and a small radius. So you can have spherical coordinates, but I'm not sure you can have toroidal coordinates for a 3-dimensional space. The spherical coordinates don't have any redundancy. You just have theta, phi, and r. You have latitude, longitude, or is it the other way around, and radius, and that gives you access to all the points in the space, the 3-dimensional space. But ordinarily, if you have some sort of toroidal structure on the space, then any point has a huge number of different... It could be on the inside of the torus at an opposite small radius, an opposite... How do I say this? Obviously, if you've got theta, phi, and R1 and R2, then you have some kind of multiple descriptions of any given point, because you've got this, you can't prefer, what is it, because you've got a redundant coordinate basically, but there's a bus stop opposite. Yeah, if you think of trying to kind of foliate the space in this room with surfaces of donuts of different sizes, all centered at the same point and lying in the same plane, then obviously there are lots of donuts that you could describe which have points that touch. So you end up with a kind of multiple sheets of multiple different sized tori. But if you do the same with a sphere, then if they're all centered at the same place, then the only time two spheres touch is when they touch all over and they are really the same sphere. But in the case of toroidal surfaces, there's this, it would be quite pretty, really. There are all these different ways, different orientations that these things would kind of peel off in different radii, different curvatures. So the subspaces would all have different curvatures given from a given point. So the coordinate system is nothing like, there's no unique way of specifying a given point, because you can't say which of the surfaces it's on when it's on all of them, but they are all different surfaces. So I guess that's why you don't hear about toroidal subspaces of a given other space. I'm not doing very well, am I? So what was the other thing I was thinking about? Jade, the video on electromagnetism is really good, because you get a real thing about if you have a volume here, any volume that covers this magnet as a whole will have the same number of magnetic field lines going in from, say we say that in is from north to south. It will have, whatever sphere you put around this magnet, it will have the same number of flux lines coming in as it has leaving. So the magnet's always the magnetic flux is always continuous, only if you cut the magnet. But if you cut a real magnet, what you end up with is like a magnet. You end up with two magnets, and their north and south poles are separated. So you can think of these field lines as little cut magnets all the way around. Because that's what the iron filings become like. They become like little magnets. And there's this, because you can get separate positive and negative charges, but because they're called monopoles. A positive charge is a monopole, and a negative charge is a monopole. Because we can separate them. But you can't do that with magnets. Magnetic monopoles. Nobody's managed to make one. But some physicists study them in terms of equations and try to, I don't know what they're trying to do with that. But I was thinking about charged dipole charges. There must be a similar rule about dipole charge. And maybe that's where the thing about ions, dipole ions and cations comes in, because in the case where the charges aren't equal and opposite, you have net positive charge or net negative charge within some shell, and therefore outside that shell, the space inside is a monopole. Do you see what I mean? Because you've got this missing electron, therefore it's a positive charge inside the shell, whereas you can't do that with a magnetic thing. If you break it, you always kind of break it in two, in terms of the two parts are always balanced, whereas somehow if you break an atom, you can break off a quanta of negative charge. But you can't break off a quanta of magnetism. I liked this analogy. There was a book, a Buddhist, Tibetan Buddhist book about mandalas, and Victoria Ryder showed the diagram from this, and what it was if you have an iceberg under the water, it's a big irregular shape, and it sits with most of its mass underwater and a little bit out the top. But the way it works is kind of the center of mass is always below the water. And so if you break the iceberg in some way, whatever way it breaks, the pieces individually kind of float up to the top, and then their centers of mass end up positioned right, and so the whole system goes back into balance with these separate parts. And you have each one of those is a whole with a little bit above and a little bit below in the same proportions as the larger one. Maybe the magnets do the same thing. There's something whole about a magnet, even though it has two poles. When you break it, the little parts are magnets. And that's not the case with an atom. When you break it, the two, I guess they want to try and get back together again because they're opposite charges. But there's this phenomenon that happens at large scales which is called like attracts like. And when you look at mixtures of positive and negative charges, the negative charges kind of want to all get close to the positive charges, and the positive charges want to all get, well, and the positive charges all want to get close to the negative charges. And so you get this clumping. It's the attraction of the positive charge that pulls all the negative charges together. In a way, even though they have a kind of natural repulsive force between them, they balance this with the attractive force of the positive charge. So, in the case of magnets, it's as if there's the integrity of the magnetic metal, or the magnetic stuff, material, is kind of holding something together, and only the magnetism as it escapes. I don't know how to say this. It's like you're squeezing, and you're squeezing it, and all the magnetic flux is all. But it's because you're squeezing so hard. If you let them go, if there was nothing holding them together, which is typically an electric chemical bonds or a crystal lattice or something like that, don't know what happens to the magnetism. But magnetism is supposed to be fundamentally produced by spin at a quantum level. But it all gets a bit iffy because nobody really knows what spin is in quantum mechanics. But you certainly get spinning magnets and in electric motors and things. And that's what all of that stuff is. So we're back to Grant and Phillips. That's what all that theory of a magnetic dipole. So when current, this is in Jade's video, when current travels in a loop, it creates a magnetic flux. And as the flux changes through a conductive loop, it generates current, and so it's an equal and opposite. And Gerald Sussman gave a talk with Hal Abelson at a programming conference a few days ago, and he talked about a connection with kind of programming languages and the way a programming language is interpreted and the way Maxwell's equations are interpreted in physics. There's a very similar parallel which allows you to actually describe systems of electric and magnetic currents as actually parts of a program that's running out in the world, that where these circular cause and effect loops are all controlled in the same and in a similar pattern to the way that circular cause and effect in a computer makes the program evolve. And he's been, Gerald Sussman anyway, has been for years been using computer programs to describe electrical circuits. And he's been using it as a way of teaching. So instead of teaching students directly, he says, look, you have to kind of run this program to analyze a circuit, and I'll show you the program, and that's how you can learn to analyze circuits. So he kind of programs his students. He teaches them programming and then shows them a program and says, this is how you analyze a circuit. That was good fun. Thank you, Jade. It was very thought-provoking, your three toruses idea. I don't even know if I got it right.